Hi, my name is Matthias Voigt, Design Lead at the Special Projects Group at Epic Games. Welcome to our talk about The Matrix Awakens, blurring interactive and cinematic experiences. We are excited to share some details into how we created the chase section of the demo, as well as parts of the open world. In my section of the talk, I'm going to focus on how we created the interactive parts of the demo. You'll also hear from Jeff Ferris on behind-the-scenes technical details. Colin Benoit will talk about how we created the cinematic parts of the demo, and Dan Reynolds will talk about the audio. The Matrix Awakens is free to download on PlayStation 5 and Xbox Series S and X. A content sample that includes the entire open world city will be released later this year. We're hoping you've had a chance to play our demo, but just in case, here's our trailer.
Hi, I'm Thomas Anderson. Like many of you, I work with computers. But computers are also mirrors, reflecting back who and what we are and the choices we make, the worlds we build. You still got it.
Like riding a bike, they say.
As you can see, The Matrix Awakens seamlessly marries photorealistic cinematics with similarly photorealistic interactive sections. Everything you see in the demo, except for a couple of intentional live-action moments, is real-time, where the cinematics run at 24 frames per second and the interactive parts run at 30 FPS. We output a full 4K signal via Temporal Super Resolution, and the entire demo takes place in an open-world city that we created procedurally and that spans 16 square kilometers. Sequencer is the foundation of the entire Matrix Awakens chase experience. The entire demo is one sequence, but we don't consider all of it to be the chase. We call the initial part the wake up, and we enter the chase as Neo and Trinity are entering the city and start talking in the car. We can drill into this subsequence right here, and we can take a look at that moment. Sequencer allows us to organize all content into subsequences, which can contain additional subsequences as well as the actual work.
What just happened?
Using subsequences allows us to manage file collisions and follow a common editing paradigm between the different disciplines. Working in Sequencer is also very interactive. Notice how, as we scrub and move the car along, we can see our location update on the world partition map on the right. We can look at the gameplay cameras as well, of course. Here we have the shooting camera setup that we used during the underpass section of the demo. If you're wondering why the car isn't moving here as we scrub, we'll get to that in a second. The chase ends with us shooting down the helicopter, which leads to a big explosion. If you want to take a look at the highway collapsing, we can even scrub a real-time preview of that destruction. Everything in Unreal Engine 5 is interactive, which of course meant that we wanted to make this demo interactive as well. The aesthetic goal of our demo was to make you feel like you're playing a cutscene, with seamless transitions in and out of interactivity, keeping the same audio-visual fidelity all the way through. We wanted to build up to the open world. We start as a Digital Humans demo, transition into the cinematic chase experience, to then release you into a fully open world. We wanted the chase experience to be immediate and satisfying, with no need for tutorials. We knew that many non-gamers would play this demo, so the interactions and control scheme had to be very simple, yet rewarding. We settled on shooting out tires and crashing cars as a visceral way to get rid of the agents, who are notoriously difficult to shoot from a distance anyway. These crashes were satisfying and help us illustrate the dynamic nature of the demo. The cars in our interactive sections are a great example of the problem space we were operating in. We had to create cars that seamlessly integrated into the linear, photorealistic portions surrounding our interactive sections. Animating these cars wasn't feasible, because the cars didn't drive deterministically. We discarded a full AI solution early on as not feasible and not needed. So we needed cars that were easy to control, looked as good as the cars in the cutscenes, and had realistic touches like a full suspension. We settled on an approach in which we could animate the path of the cars, but could also run our chaos physics system. To do this, we authored multiple tracks that were animated by our cinematic animators. This kept the quality consistent. Here you can see 3 tracks from the initial shooting section. Each one can be used by a car in pursuit. But the cars you see here are a bit of an illusion, because we did not actually animate our chase cars in Sequencer. What we did animate was a lightweight stand-in blueprint object, shown here as a cube. The stand-in has a constraint that a car can attach to. This is the object that we keyframed. You might think of it as a ghost car that drags along the actual car that you see at runtime. The visible car you see at runtime has a fully simulated chassis via our Chaos physics system. If we enable our runtime debugging tools, the setup becomes clearer. We can see the invisible stand-in as a cyan box below each car. This is the animated object that drags the actual car along. The stand-in creates a slot that a car can occupy. The red boxes tell us that a slot is taken. A runtime drama manager directs the action. It makes sure that all slots are filled, that cars keep rushing us using the middle track, and that agents jump towards us. This made each playthrough unique, but within well-defined boundaries that we can control. As we crash cars by shooting out their tires, a new car from the side moves into the center slot. To switch tracks, we detach the car from its constraint, lerp it over to the new position, and reattach. The entire system for animating and simulating cars was created by one of our animators in Blueprint and Sequencer. To make sure we don't run out of cars, we backfill by spawning new cars out of sight, lerping them towards their slot, and constraining them to the new track. We do this far enough back so that the player hopefully never notices the backfill. For the final machine gun section, we realized that we couldn't backfill fast enough, because we wanted to make the gun extremely powerful and to take out cars rather quickly. So we added additional perimeter tracks that allowed us to spawn the car behind the camera. These cars could then fall back until they were in view and join the fray. Agent jumps are dynamic. Any agent can jump any distance and to any destination via our new motion warping feature. This allowed us to make the agents rush the player whenever, and however frequently, our highway shootouts required. Frequency and aggressiveness were also controlled by our runtime drama manager. To allow the player to crash cars, we created a system that let us make any object targetable via components. Our system registers hits, spawns signs and feedback, and triggers some permanent damage to provide persistent feedback. In some cases, we also triggered an additive swerve animation to show the player that they were making progress when shooting at the car.
These guys just don't give up.
The actual crashes, which give the player a feeling of impactful interaction with the world, were triggered from Blueprint and called into our universal car damage system. Once the tire blows up, we take the car off sequencer control by breaking the constraint and tell it to crash. We have a library of initial crash parameters, but what happens afterwards is unpredictable and unique to each playthrough. To learn more about how the car crash system works, check out the talk Creating the Vehicles and the VFX. We use Unreal Engine 5's world partition system to automatically stream the city around us. We wanted to give the cinematics team all freedom to scout this large and interesting city, as they would on a live action shoot. They were able to pick the best locations for each scene, even if this meant large spatial jumps. Because of this, we had to support invisible and seamless teleports over long distances without the player ever noticing the jumps. Let's take a look at just how much we do teleport around.
Keep them off us. You drive. I'll shoot. You boys are gonna get a kick out of this. Come and get it.
We were able to do these teleports using streaming sources. Streaming sources are components that define a position in the open world and trigger the loading of cells around them. You can see an example here from our Valley of the Ancients demo. The early access version of Unreal Engine 5 already supports multiple streaming sources, but for the chase, we had to push our streaming source setup even further. We use 3 different streaming sources in this demo: the main or hero streaming source, a prefetch streaming source to set up teleports, and a touch-up streaming source to make the city look as stable as possible. By default, Unreal Engine 5 attaches a streaming source to the player, but we never actually see the chase from the player character. We always see it through a camera. Our first step was to remove the default streaming source from the player character and use a bespoke streaming source that follows the camera instead. This way we don't have to worry about odd streaming bugs as we possess and depossess various versions of the player character, which could cause streaming to jump around, if even for just a frame. This hero streaming source is a simple actor with a streaming source component, which can enable and disable itself as the main world partition streaming source. Then attach this actor to the car via sequencer and call into it via a sequencer event track. To seamlessly teleport around, we use a second prefetch streaming source. This is an instance of the same class as the hero streaming source. This source is placed where we go into teleport, and we activate this source 3 to 5 seconds before the chase approaches a jump around the city. With the second streaming source active, all necessary cells will be loaded at the location we teleport to by the time that we teleport. One issue we had to solve for was memory. Multiple streaming sources can load the highest level of detail of the open world in multiple places, but of course that takes up additional memory. The chase stretches memory of our supported platforms to the limit anyway. We simply do not have enough RAM to load 2 full sections of the city at the same time. We solved this by adding support for custom streaming source shapes. A circular streaming source is only required when a player has full control of the camera and could quickly turn around. Whenever we walk around the open world, for example, we need a circular streaming source. And the same would be true for a feature like fast travel, because we cannot predict where the player will look at after the teleport. This is where our chase interaction and camera paradigm helps us out though. We don't need a circular streaming source because we know rotation of the camera at all times. Knowing the camera direction of our upcoming teleport location allows us to create a streaming frustum and pre-stream precisely the part of the city that we will see after each teleport. With that reduced memory load, we actually fit into RAM. Our final type of streaming source is a touch-up streaming source. We found that signature skyscrapers would occasionally switch LODs at inopportune times while we were driving along the freeway. A world partition world is very stable by default, but we wanted to avoid even small pops in the distance if we could. We strategically placed one of these streaming sources, which were similar to the ones we've already discussed and also had a custom shape, to pin building LODs in memory at particular times. Now with all of these techniques established, let's take a look at all of these approaches in action by looking at the game doing an actual teleport. The following is an unlit debug view in which we've turned off all the H-slot buildings so that we can really see the parts of the world partition that are streamed in around us.
Shoot the tires. Say no more. Keep them off us. You drive. I'll shoot.
Custom streaming source shapes will ship with Unreal Engine 5.0. Now keep in mind that you only need to do what we've just discussed in extreme cases, like doing totally seamless fast travel. World partition looks very stable by default, and world partition also loads very quickly on teleport. A typical teleport, for example for a fast travel option in an open world game, might only take around 3 to 5 seconds. We've talked about world streaming. Let's finish up with object memory management. The chase uses data layers to manage spawning of objects in their lifetime. We typically have multiple data layers per section, which we activate a few seconds before the start of a new section to spawn and despawn all relevant objects. To control spawning manually, we first take the objects of the world partition runtime grid and assign them to a data layer instead. We then manage data layer activation, and thus which objects we expect to be in memory via sequencer. Data layers are an easy and powerful way to stream objects for missions or set pieces that aren't permanent parts of the regular open world. This is how we overlaid the entire chase on top of the open world and could clean up after it without leaving a trace. Once we were correctly streaming all the objects in the world, we needed to account for one more source of memory consumption, class default objects, which are essentially a template object that Unreal Engine uses to instantiate actors. We had to make sure that our class CDOs were loaded into memory before we were spawning the actual actor in the world. There are several ways in which CDOs can be loaded prematurely. On the chase, event keys cause class CDOs to load as soon as the master chase sequence was opened, even though our intention was to control the memory footprint of these classes via data layers. There are a bunch of different approaches we could have taken here, but our solution was to pass the object as a generic actor instead of its actual type, and then making interface calls on that actor. This kept the actual class's CDO, as well as that class's entire reference chain, out of memory. I now pass it on to Jeff Ferris to talk about more engine features and technical details.
Hello, I'm Jeff Ferris, Technical Director of Special Projects here at Epic Games, and I'm going to dig in a little deeper and talk about some of the underlying systems we used to build The Matrix Awakens. So when we started this project, we knew we wanted to embrace a systemic approach. We wanted our technology to be flexible so we could have some room to maneuver as we iterated on the design. We also knew we didn't have a huge team. The tech was going to be responsible for some heavy lifting if we wanted to realize our ambitions. And finally, we wanted to build technology for more than just this demo. We wanted as much functionality as possible to flow back into the engine and end up in users' hands once Unreal Engine 5 was released. The first system I want to talk about was a cornerstone of the entire project, and that's the chaos physics system. There are many aspects of chaos physics that we relied on, as nearly any UE5 project would, such as basic collision detection, collision filtering, scene queries, or rigid body simulation. But given that we were set in a city environment in the Matrix universe, we wanted to tackle realistic vehicles. So the Chaos team went to work on an updated vehicle physics solver, and the result is a new component called the Chaos Wheeled Vehicle Movement component. It's a highly configurable vehicle solver capable of producing stable and very realistic simulations, and it gives designers a high degree of control over the look and feel of the sim. It can handle varied wheelbases, including different numbers of wheels and wheel sizes, as well as articulated vehicles like the semi-trucks with trailers you see on the freeway in the demo. And of course, they can be driven by the player. We knew, though, that once we put drivable vehicles in players' hands, that not everyone would strictly follow the rules of the road. So another challenge we tackled early on was how to come up with a vehicle destruction system that was both dynamic and satisfying. Chaos was a key component here as well. We'll have many more details in another talk, but I'll give a brief version of how this worked. Each high-res car model was imported as a collection of nanite static meshes, which enabled us to have both enormous geometric detail per car and a high number of vehicles on screen at once. But nanite currently has a limitation where we can't deform a nanite mesh, so we also imported the crushable parts of our vehicles in the traditional way as rigged skeletal meshes, complete with LODs for efficiency. These skeletal meshes had a physics asset that contained a set of censored chaos bodies, which used a newly implemented type of constraint called a plastic constraint, which allows for one-way deformability. This gave us a rig we could deform without having it spring back to its original state. These bodies also drove a control rig, which was set up per vehicle to provide believable secondary deformation, such as a hood buckling upward as the front end was pushed in. So during an impact, what happens is that the part of the car that needs to deform swaps from the nanite representation to the skeletal mesh representation, and then the rigid body simulation pushes the physics bodies around into new positions. This drives the major joints in the skeletal mesh along with it. This in turn drives the vehicle's control rig, which moves around even more of the joints in the rig, and gives us the final deformed pose of the mesh. On top of this, we did some work in the materials to add more micro detail, like adding higher frequency crumple maps and paint chips. Check out the vehicles and effects talk for more details on this. So overall, this system lets us get believable and satisfying deformation patterns, while being general enough that the deformation matches the type of impact that the car experienced. And that feels good as a player, because it matches expectations. This was huge for us when it came to authoring the chase sequence. We didn't need to worry about custom handling for the various things the player might shoot at, or the many ways cars could run into each other. Letting the player weapon damage the cars became simple. We just gave a small physics poke at the impact point and slapped a bullet hole decal on there, and that's it. The car would react appropriately, and we didn't need to worry about it. And once a car had absorbed enough damage and it came time to crash it, all we had to do was release it from its scripting constraint and let physics take over. In our case, we did end up giving the cars a little extra physics kick when this happened, which helped boost the drama and take the experience a little more over the top. As an extra bonus to this approach, every playthrough ended up being unique, which was a cool experience for the player. One more chaos system I want to highlight quickly is Chaos Cloth. Parts of our demo featured enemy agents wearing suits standing on cars, speeding down a freeway, all while standing very close to the player. Obviously, it would be an extremely windy environment, so we needed the cloth to animate in order to sell that wind and make it believable. So we ended up taking two different approaches here. We began with a high-res cloth rig. This turned out excellent for situations where high fidelity was needed, such as when the agents were on the trunk of the car near the player camera. But we found that farther from the camera, an approximation of the simulation done in the vertex shader was more effective visually, since the lower LODs had less detail in the model. Plus, it was more efficient. So we set it up so we could blend dynamically between the two as needed, which was a great approach because we could adjust the blend on the fly and avoid any discontinuities as the agents moved around the scene. So while we're talking about the agents, I wanted to show off another new feature we wrote, this time for the animation system, that we call ballistic warping. Matt mentioned this earlier as well, but I wanted to call it out as a key tool for authoring the parts of the demo where the agents hop from car to car. What ballistic warping does is takes an animation that's intended to simulate flight along a ballistic trajectory, like a jump animation, and then conforms it to a different arbitrary trajectory. It performs warping in both space and time so the animation looks as correct as possible throughout. So as an example, a jump animation that was authored to cover 2 meters could be used at runtime to make a character jump, say, 3.5 meters, and it will still look spot on. The end result here was a great win for our team. The designers didn't need to worry about setting up specific situations where jumps could be allowed, and the animation team didn't need to produce or manage a massive library of jump animations for every approved jump distance or height differential. We had a small set of jump animations for variety, but then we warped those at runtime to match the exact situation at the given moment that we needed it. So if an agent was jumping to the hood of a low sports car nearby or to the roof of a tall SUV farther away, it just worked and it looked great. I want to note real quick that this is still an experimental feature in Unreal Engine, so expect to hear more about it in a future release. Next, I want to talk briefly about the world partition system, a key new feature in UE5 that enabled us to play in such a large-scale open environment, not to mention being able to build it in the first place. Matthias talked earlier about how we worked with streaming during the chase, but I wanted to highlight some of the workflow wins we had as well. World partition turned out to be very effective for us, so much so that the entire demo takes place in the same loaded world. From the opening cinematic shots, through the chase sequence, and all the way to the sandbox at the end, it's a single map. World partition handled all the spatial partitioning and runtime streaming for us, with no need to manually manage which actors lived in which cells or what cells need to be loaded when at runtime. And on top of that, we used a feature we call data layers to control which sets of data were allowed to be streamed in any given context, which meant we could smoothly transition from the intro cinematic to the chase sequence to the sandbox, or just load directly into any one of those without ever having to do a hard load or a map transition. World partition also improved workflows and iteration times massively for our content teams by allowing them to limit the data they had to load while working in the editor. They had the control to load only the cells or layers they needed to work on at any given moment. Plus, the one file per actor feature of world partition massively reduced asset contention, which meant more folks working in parallel in the same world without getting in each other's way. This was a big deal for us. I also want to point out that world partition was very flexible for us, giving us tons of control over things like streaming cell sizes, loading ranges, or the ability to prepare for upcoming camera jumps, like Matthias discussed earlier. Having these tools was indispensable while optimizing to hit our performance and memory targets. One problem we ran into with our cinematic style content was handling camera cuts. Nanite and our virtual texturing systems in particular are very powerful and very, very good at using memory efficiently, but they rely on GPU feedback to do this so well. They take great advantage of the fact that the camera typically moves only a short distance for the vast majority of frames. But what this means is that when the camera does move significantly, it can take a couple frames for the proper data to get loaded, which causes artifacts in the meantime. So we needed to give these systems some additional help to really nail the image quality around camera cuts. What we ended up doing was using our offline frame rendering system called Movie Render Queue to dump out pre-streaming data for Nanite and virtual textures. Then we added a custom track to Sequencer that would consume that data and provide timely loading hints to the renderer so the proper data could be loaded before a camera cut happened. Note that this solution is also currently an experimental feature, but expect to see more of this in an upcoming release. Next, I want to touch very briefly on our crowd and traffic systems. We set out to create a vibrant and believable city environment, and these systems were a huge part of that. They give us a city full of life that was enjoyable to be in. They were also an opportunity for us to really lean into the idea of scale in our simulation. So our AI team went and built what we call Mass AI, an AI system that was built from the ground up with the intent to be able to scale to huge crowds of AI agents. In The Matrix Awakens, we populated and simulated the entire city, not just a bubble around the player. To give you an idea of that scale, we shipped the demo with 35,000 crowd members roaming the city and 17,000 vehicles actively driving around and generally obeying traffic laws. Mass AI is very efficient and highly parallelizable, so all of this ended up costing us only about 6 milliseconds on the game thread on our shipping platforms. Now, these systems were great in the open world city, but they turned out to be a critical tool for helping us author the chase as well. Colin's going to talk more about this in just a minute, but we saved ourselves tons of time by leveraging the crowd and the traffic and even the drivable vehicles to get great-looking linear content with minimal effort. We love this idea of using real-time and interactive simulation systems as efficient content authoring tools, and really, I think we're just scratching the surface here. Next up, we have Colin Benoit, who's going to talk more about how we put together the linear content in this demo. Thanks so much for listening.
Hi, I'm Colin Benoit, lead cinematic artist here at Epic Games. Building on what Jeff and Matthias just discussed, I'm going to talk about how we use those same systems to construct the cinematic portions of the demo. How do we approach building an interactive story that looks and feels cinematic, all playing in real time in the engine? Well, first off, we need a story. Since The Matrix is essentially a computer simulation, it seemed like the perfect match to show off the power of UE5. After some initial exploration about what would work best narratively to demonstrate the latest features of the engine, we partnered with Lana Wachowski, the director of The Matrix Resurrections and co-director of the original trilogy, who provided a script as well as footage from a live-action shoot, which actually ended up in the final demo as part of the wake-up sequence. We settled on a story involving Trinity, looking like she just stepped out of the original trilogy, jamming through the streets of our megacity in a badass muscle car with a young trainee by her side. So we needed to create an exciting car chase. On a film, you would hire a stunt crew, plan out the various beats, and then film those beats in specific setups. So we thought, why don't we do the same thing? Although instead of a stunt crew, it's a person with a controller. So first off, we needed our stunt vehicles. For that, we had access to a suite of cars under development that were using the new Chaos Vehicle Physics Solver that Jeff mentioned earlier. It meant we could go blasting down a street, pull the handbrake while rounding a corner and get a very realistic looking result. It even allowed us to tune the suspension for certain driving situations. To capture the action of our stunt vehicles, we used Take Recorder. We could slate the action, much like you would for a live-action film, and then shoot multiple takes and review them immediately after. This allowed us to stand up a sequence very quickly and iterate with very little delay. So we could set up the action, for example, adding traffic for our hero car to weave through, and just roll on a few takes. If we crashed into another car or a concrete barrier, no worries, just reset to 1 and go again. No one was harmed in the making of this action scene. Each take was immediately available for review and editor using Sequencer. This allowed us to evaluate and choose circle takes. We could shoot as many takes as needed, and we could even adjust the animation after the fact by adding additive transform tracks. For example, if we wanted the car to fishtail more than what was captured, we could exaggerate the Z rotation. Using Take Recorder, we could also create what we call layered takes. This involved recording into an existing take, essentially layering action to build up a scene. The best example of this involved recording agent cars chasing our heroes. This gave us unique motion for all the principal vehicles, adding to the realism. We could even record traffic reacting to the hero and agent cars zipping by. And again, the recordings were all available in Editor. This process saved us an incredible amount of time laying out the scenes, and the fidelity of the resulting vehicle animation was well beyond what we could get using keyframed animation. The next step was to film the action. Now that we had a continuous beat of action in place, we could film that action from multiple camera angles, much like you would to cover a live-action stunt. We used a cine camera actor essentially matching an Arri Alexa with a 240 center crop and a fairly standard spherical lens kit, similar to the Super 35 setup they used in the original trilogy. Using reference from the Matrix films, as well as other Hollywood car chases, the camera lensing and movement was chosen to mimic live-action cinematography, but with a decidedly Matrix flavor. Subtle dolly zooms, jello time, and of course, bullet time. All the non-interactive cinematic sections played at 24 frames per second, including the wake-up intro section. This was an aesthetic choice to match the traditional frame rate of film, meant to achieve a more cinematic look. The interactive sections, however, ran at 30 frames per second. Car crashes feature heavily in the interactive sections of the demo, but we needed a handful of crashes in the cinematic sections as well. For this, we had the ability to dynamically flip and crash cars with a hotkey. We could then record those crashes to populate the mayhem around the hero car. Using all these techniques, from the layered recordings to the car crashes to the cinematic language with the camera to the addition of some early stunt mocap, we were able to visualize the interactive sections as well. This early viz allowed us to get a sense of the action and to confirm it would work in the overall demo flow. It also gave the designers and other team members something to reference as they worked towards creating the jaw-dropping version you see in the final demo. We really wanted it to feel as if you were inside a scene from a film, but able to reach out and affect it, to give the player that moment of, wait a second, I can play this thing? To continue with the parallels of live-action filmmaking, now that our stunt driving was in place, we could use similar techniques to put the principal cast members into vehicles for the dialogue scenes and then film them. All the character motion and dialogue was captured and processed using technology and workflows developed by 3Lateral and Cubic Motion. For a deep dive into how the digital humans for The Matrix Awakens were created, check out the Creating the Characters Tech Talk. Now with the characters inside the vehicles, as they're flying down the street, all running in real time in the editor, it was easy to experiment with alternate camera angles, or even reshoot vehicle action to better flesh out the story. Some of this made it in, while some was left on the cutting room floor. Another parallel with live-action filmmaking. With the vehicle driving down the street or along the highway from a previous take recorder shoot, we could now film long takes of a single camera setup. For example, singles and overs on Neo and Trinity, delivering all the lines for an entire scene. We could then operate the camera to follow the character's motion, just like a live-action camera operator. Each of these camera takes could then be immediately cut together in Sequencer or rendered out and edited offline. Any editorial updates in a nonlinear editor could then be imported back into the engine using the XML importer in Sequencer to conform the in-engine cut with the offline version. The lighting was approached from a live-action mindset as well. Thanks to Lumen, the majority of shots could be lit much like a film relying on natural light. We used a single directional key light and a sky dome, adding an additional rim or fill light only when necessary. We could then adjust the sun position per shot. To really show off the power of Lumen, it was discovered that we could place simple cards just off camera to act as bounce surfaces, a technique that's used all the time in live action. Even better, it was essentially free from a performance perspective. Overall, we used a mix of techniques: ray trace lights, virtual shadow maps, Lumen, all at once in lighting the demo. The wake up section at the beginning of the demo is also based on a script from Lana Wachowski. The visuals are a seamless integration of live action photography and real-time virtual cinematography. The opening scene of Neo in his apartment, which is nearly an exact match to the scene from the first Matrix film, is entirely virtual and playing back in real time. It was a good way to throw the audience off, especially with live-action photography showing up right after it. It's important to note that the entire demo, including this apartment scene, the white construct scene, and rooftop scenes, all lived inside the same map as the 16 square kilometer megacity. This allowed a seamless transition from Wake Up to the chase to the open world sandbox. As I mentioned, this sequence did have live-action photography, the only sequence to have real footage in the demo. Like the entirely digital sections, these were also playing back in real time in Sequencer, this time using a media track. This allowed artists to see the footage in-engine as they worked on surrounding shots. It also made managing the whole process easier, with Sequencer driving the entire demo. The systems developed in Unreal Engine 5 were key in allowing us to pull this demo together with a very small cinematic team. My hope is that these tools will give other content creators working on narrative pieces across linear and interactive media immense creative freedom, allowing them to work quickly, get great-looking results, experiment, and even stumble on those happy accidents that are such a great part of live-action filmmaking. Now on to Dan to talk about audio.
Hi, I'm Dan Reynolds, Senior Technical Audio Designer with the Unreal Audio Engine development team here at Epic Games. And in this part of the presentation, I'm going to discuss how MetaSound's next-gen features empowered sound and music designers to create cinematic audio experiences on The Matrix Awakens. In the interest of time, I'm going to highlight just a few meta sounds from the demo that best expose features and design approaches that would have otherwise been impossible to achieve previously. Let's begin by taking a look at the guns from the chase sequence.
Okay, how about the big gun? Thought you'd never ask. You boys are gonna get a kick out of this. Come and get it!
Traditionally, one of the advantages that film and television has had to Unreal Audio has been that soundtracks are not constrained by video frame rate. Cinematic audio is continuous and allows for sounds to be placed between video frames, which is especially important when there is some kind of ongoing mechanical or musical rhythm. However, in Unreal, commands to place sounds stem from interactive logic and player input, and thus are constrained by the limitations of the video frame rate and the game thread update periodicity, which for Unreal is the same thing. As you can see here, video frame rate could be anywhere between 24 to 60 frames per second, depending on your project specs. Similarly, the audio logic thread, where sound cue timing is evaluated, is lockstep synchronized with the game thread for garbage collection purposes. This has posed a challenge to sound designers when creating machine guns with a higher rate of fire than the game thread update, or one where maybe the periodicities don't quite match up. As a consequence, sound designers of the past had to either implement a slower rate of fire or design their gun sounds with loops edited in their linear editing environment. For the former group, this meant constraining fire rate to video frame rates, which could create drift in frequency when the render time goes up, or other possible issues, say on lower-end platforms with limited resources. On the other hand, the group implementing loops ends up introducing a sort of cyclical sound to their design, which is not always desirable. And they still have issues masking the transition between the loop stopping and maybe the final ring out of whatever the sound is. However, both the audio render thread and meta sounds can receive data updates from gameplay at a much higher rate, depending on your platform specs. And meta sounds can play sounds using triggers which are sample accurate, supporting a resolution of up to 48,000 times per second. The same resolution as cinematic sound editors would have in their linear editors. If we take a look at the meta sound, we can see that the meta sound is split up into multiple parts here. We have the gunshot body, the mechanical layer, the tail, the sweetener on the first shot. And all of these coming together in a mixer. On the left, we have the on-play input, but then we also have a stop firing input. If we were to play this, we get that nice tail. And then you'll also notice this fire rate parameter. So here is the delay between shots. We can adjust this to maybe 1/10 of a second instead, so it slows down. Or maybe we feel that the shot should be faster, let's say twice as quickly. As we can see, sample accurate triggers allow meta sounds to play sounds at the highest audio retiming resolution possible. We're able to take advantage of non-repetitive design patterns, which, in this case, allows chaining one-shot samples without relying on loops. That leads to faster iteration. The loopless design provides flexibility in adjusting event frequency to taste without re-editing the sound material. We don't have to go back to the DAW or linear editor to re-edit the loop. And then the high resolution maintains consistent timing and feel, so we never drop that. We never feel the gunshots drift. They're always on time. Additionally, custom trigger inputs via the parameter interface allow for a more robust communication between interactive logic and the design. This empowers designers to create more sophisticated and flexible designs than just play a sound, stop a sound. In this case, meta sounds can stop gracefully, with tails or even pre-authored outros. Compared with film or television, interactive experiences require significantly more content in order to drive user experience for hours and hours of playtime. Now, one of the most important ways to facilitate this in the production is to reuse, recombine, and remix source material. Taking a look at the nighttime music in the sandbox, we can actually see this in action. We have let's play it. We have stems, brass stems. We have strings, woodwinds, synthesizers, pads. Everything is essentially components that were delivered by our composer for other pieces. And here we have effects being applied, delays, filters. And so, as you can see, all of this is essentially being redesigned right here in the editor in the meta sound. From that example, we can really see that meta sounds is an in-editor sound design environment. It allows sound designers to combine and recombine raw assets, create new variations, or in some cases, brand new designs. And case in point, we were able to take stems and parts from the delivered music mix and create remixes to extend the usability of the original music material. More than that, built-in music utilities and meta sounds help music designers build custom music systems quickly. Our audio director was able to create multiple music remixes for the sandbox and the countdown screen in just an afternoon. And finally, a challenge that is almost completely unique to interactive experiences, where we have a very large sandbox environment, completely populated with NPCs. In this case, 20,000 traffic vehicles, simulated by the Mass AI. And we only had about a dozen makes and models of individual cars. So there was a very high likelihood at any given time dozens of vehicles would be within hearing range, dozens of vehicles, maybe even of the same make and model. And to top it off, because it's possible to track vehicles from a great distance, we had to figure out some way to ensure that each individual instance would have its own unique variation. So if you re-encountered that vehicle later on in the map, it had to sound the same. If we take a look at the meta sounds, we can actually see how this was accomplished. First of all, it's worthy to note that the NPC vehicles, they're a simplified sort of vehicle model. There's a recorded engine component that does a pitch blend between idle, low, and high engine loads. But then we also have a synthesized noise component and a synthesized sub component. And those three components can get mixed into different ways. So here we have, we have the seed value as -1, and that is essentially, that means no seed. So every time I play, it will sound slightly, each variation will sound slightly different from the last. Obviously, it needs to sound like the same make and model, But this is a variation within that. And it's just, all it's doing is just changing and tweaking these threshold ranges and the mix it and blend between them. And so what's really cool is that if we actually enter a seeded value, like, I don't know, 232, then it will always sound the same. This is because metasounds are built from the ground up with procedural audio generation in mind. As such, every native random node can intake a seeded parameter. So I was able to set up random ranges for each vehicle, so each sound instance would have its own custom mix of the various vehicle sound elements. In order to satisfy persistence, I was able to coordinate with the Mass AI team to feed the specific AI agent's ID integer in as its seed. So every AI vehicle ends up having its own custom random ranges that persists and is consistent each time the listener comes back in range of that AI vehicle. Additionally, metasounds are rendered in asynchronous tasks like normal decoded audio. So, assuming your CPU is not saturated, you should be able to render many metasounds at once with no visible impact on your main threads. Conservatively, we were able to render as many as 30 of the closest vehicles to the listener at any given time. And finally, it can't be overstated, metasounds support a variety of parameter types in its scripting interface. I was able to feed each vehicle metasound an integer 32 seed on instantiation so that each vehicle could have its slightly unique sound. And I was able to continuously feed in velocity as float data into the metasound instance, simulating continuous changes in engine load. And that concludes the audio tech portion of this particular talk. Thank you for hanging out with me. I hope it was useful and interesting. Big thanks goes to Zach Balika, Noah Landis, Adam Block, Aaron McLaren, and the magnificent Audio Engine team here at Epic Games, as well as the lovely people at Formosa Interactive, without whom making this Matrix Awakens demo would have even been possible. Thanks again, and I hope you get to check out Unreal Engine 5 real soon.